Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on solving ordinary differential equations. In the previous lecture, I talked about what do we mean by solving an initial value problem for an ordinary differential equation. And we said that in an ordinary differential equation, we always have one variable and one or more functions, and the very basic case is y prime equals a function of x and y. All right, if we can solve this, we can solve basically almost all of the ordinary differential equations that we encounter in engineering and physics. And then we said that there are some common methods. The most basic one is Euler method, the forward Euler method. And implicit methods such as backward Euler method can also be used, but then because it gives you an implicit result, then you have to also solve an equation to find the value of the function. It's not just solving the differential equation. You have to also numerically solve or find the root of an equation because it's an implicit equation. And then we said that there are also other methods with higher accuracy than the Euler method. And the most famous one is RK4, Runge-Kutta fourth order, and some of its derivatives like Kashkarp, Fehlberg, and other versions of Runge-Kutta with different orders. But RK4 is the most commonly used one, so we're going to look at that. Now, for the Euler method, we said that the idea is that if I am given an initial value problem, so y of a equals y0. And we can call a x0, right, the start point. And then when we say we want to solve the differential equation, it means we want to find the value of the function y at some later point. Let's call it b, right, y of b if I know y of a. And we said that in order to do that, the very basic way or the very basic approximation is to write y prime as a simple forward approximation, y of x plus h minus y of x divided by h. And in order to do that, h basically represents the length of a subinterval. So we discretize the interval from a to b into n subintervals, and h becomes b minus a over n. And we said that we always prefer uniform partitioning because of its simplicity. And again, the reason we do that, because remember, we're solving a differential equation. That means we have to do some sort of integration. And integration, numerical integration, always involves partitioning an interval and summing some sequence over that interval, okay? So we get that, eventually we get this equation. If I know the value of y at some point x, I can estimate it at some very small interval after that, y of x plus h, which is y of x plus h times y prime, which is f of x and y. And we said that the error is not good, 1 over n. And this type of discretization leads to a sequence, y of n, that is supposed to converge to the exact value of y at that later point b. So xn here is b. As we increase n, the length of each subinterval gets smaller and smaller, and the error goes down because the error is proportional to h or inversely proportional to n. But remember that h is b minus a over n, all right? Even if I have increased n, if b increases, so if we want to find the value of the function at some point very far from the initial point, it is always guaranteed that the error gets bigger and bigger as we go farther and farther away from the initial point, right? So we need to have more and more subintervals. So keep that in mind. The error gets larger and larger or bigger and bigger as we try to find the value of the function, the solution for the function at points that are farther away from the initial point, x0 or a, okay? And we said that the idea here is that based on the method that we use, let's say here Euler method, we create a sequence that basically mimics this yn behavior, right? So we have to specify we're looking for a value of the function at some point. I call it x1 or b. And then we create a sequence that converges to the value of the solution of the differential equation, i.e. y of b, given the initial condition x0 and y0, the sequence converges to the value of the function at the point that we're looking for. And then we said that, okay, Euler has a very bad error behavior. It's very slow, therefore it's very slow convergence, and we can accelerate it using the acceleration methods that we've seen so far for sequences. And because the error behaves in a 1/n fashion, we know that it's suitable for Richardson acceleration. And we demonstrated that by looking at a very basic example. And obviously when we want to look at how good our numerical method is, we want to look at problems that we know how to solve. We have the exact solution. For example, y prime equals minus y and y of 0 is 1. So this is an initial value problem. Our f of x and y that describes the derivative, y prime is minus y, right? So this is the derivative function. And then we create an ODE solver, we give it the function, the derivative function, and the initial value x0, y0. And then we create the sequence based on the Euler method. And we want to look at the value, we want to find the value of y at 0.5. So the Euler sequence, this method creates the sequence that converges to the value of the function at 0.5. And we said that even with the 100 iterations or 100 moving forward 100 terms in this sequence doesn't give us a very good accuracy, only 2 decimal places of accuracy. And then we said that as soon as we apply a third or fourth order Richardson acceleration on this sequence, the error suddenly goes down very rapidly, right? We get more than 8-9 decimal places of accuracy. So this is just for finding the value of the function at y of 0.5 this plot, and then we can find the exact, eventually what we are looking for, y of x. So here I'm comparing the exact solution with the fourth order Richardson solution on Euler at n equals 100, and this is the x values, so x0, 0.5, 1, 1.52, all the way to 5. And remember, as I mentioned, as we try to find the solution at farther points away from the initial point, which is 0, the error increases because it's proportional to some sense, it's proportional to the length of the interval b minus a, right? And that eventually brings us here that yes, if I look at the x values, so the blue curve here is the exact solution at any x, right? From 0, which is the initial point, which the function is 1, right? y0 is 1. And then at x equals 50, the function is very small, okay? But I have calculated and plotted it here, right? So this is not the error of the function. This is the exact value of the function. And it's on a logarithmic scale. And because the solution is exponential, so on a logarithmic scale, it should definitely be a linear curve, right? It's just a line. But then if I look at the Euler solution with the even with the fourth order Richardson acceleration, we see that after passing x equals 30, the value of the solution actually starts to diverge from the exact solution. So we get a large error as we move forward in x, right? At x100, the error is even larger. So this is not good because even if we do acceleration, we still get a large error for large values of x, the values that are far away from the initial value. And the reason for that is because in my code, if you look at the Euler method that calculates the value, it gets the Euler sequence, does a Richardson acceleration, but it always finds the sequence at a fixed point, 100th term of the sequence. And because the error grows with b minus a, the length of the interval, one way to remove this problem is to increase this 100th term. So at x equals 50, I have to evaluate the fourth order Richardson at, let's say, 200th term instead of 100th term. But the problem is that then it changes from one differential equation to another, and it's really, we have to examine a couple of things, the nature of the differential equation, to figure out what is the best way to adaptively change this number, and that's not easy. But there is a very easier solution to this problem, and that's it. So I know that I want to, let's say, but this particular solution applies when we're trying to look at the, basically find the solution at many points from 0 to 50, okay? So what I can do is that, let's say I want to find the values of the solution y of x as at an array of x values, let's say 0, 5, 10, 15, 20, 25, all the way to 50, okay? So what I do is that I start from x0 and then find the x1 using Euler plus R4. But then if I want to find the value at the later point, instead of starting from the original initial point, I use the previous point as the initial point. What I mean by that is that I know my solution should return an array of solutions, right? An array of y values, each one corresponding to one x value. So I say that, okay, I copy the original initial points, initial conditions, x0 and y0. They go to x0 copy and y0 copy. And then I write a for loop, and I start from the x0 and y0 and calculate the y from the Euler at x1, y1, x1 index 1, right? But then I change the original initial conditions to the previous points. y0 changed to the new y that have been calculated at the current step, and then x0 is changed to x1 at the current step, right? So what this does is that it calculates the y at index 1. So y at index 0 is y0, and x at index 0 is x0. So these are given. And then we calculate y1 using the Euler based on the original initial condition, but then the initial condition changes, and y2 is calculated based on the y1 and x1 as the initial conditions. So this way, if you are evaluating at a large number of points, the length of the interval always stays very small, all right? And that means the error actually doesn't get large, doesn't grow large as we get farther away from the original initial point. Because, for example, when I'm solving for x equals 50 to find the value of y at x equals 50, I'm not using the initial value y0 equals 1. I'm using the initial value from the previous point that I solved, right? So this way the error always stays as low as possible, okay? So this is a very neat trick or clever trick to avoid this problem. So after finding a solution at x1, use it as the initial point or the initial condition to find the value at x2, okay? I hope this makes sense, because this is a very interesting trick that we can use. And now let's look at what happens when we apply this trick. So this is again, this is the Euler plus fourth order Richardson. So we have this, and now we are applying that trick. So when I'm solving from 0 to 50, let's say 100 points, 100 x values, at each x value I use the previously calculated point as the initial condition, and as you can see, there's absolutely no error. So we really remove this problem. And to see this more clearly in the code, I'm going to go back to Eclipse. In my ODE project, we discussed that we had this ODE class, ODE solver, that gets the initial condition x0, y0 and the y prime function, and then creates the Euler sequence. In the Euler method, we calculate the Euler sequence for a given point, Richardson it, fourth order Richardson, and evaluate it at 100. And now I have this Euler method that takes an array of x values, which are basically the later points with regard to the original initial point, right, x0. And then I want to return an array of y values, which are the solutions, right, at each given x value. So I copy the original initial conditions, and then I write my for loop. I calculate the y using Euler at some x, and then I change the original initial condition to the current values that I calculated, okay? And at the end, I return the original initial conditions to preserve them, and then I return the y array, okay? So this is how we can remove or basically try to reduce the effect of a large interval on the error of the Euler method, or in general any ODE method, because all of them, as you get farther and farther away from the initial point, the error should get larger and larger. Now in the test Euler class, we looked at the example number 1, which was looking at the Euler sequence for y prime equals minus y differential equation, and looking it at a point 0.5, which is very close to the initial point, which was x equals 0, right? So our initial condition is y of x equals 0 is 1. So if we calculate at 0.5, and let me just run it again, we see that we eventually converge to the value, and I'm applying the fourth order Richardson, so the convergence is fast, right? Now in the example 2 that I have here, again the same equation, y prime equals minus y, the same initial conditions, y of 0 is basically 1, but now I'm trying to find y of 5, x equals 5. Instead of in the example 1, I calculated y 0.5, which was very close to the initial point. Let me run it one more time. Okay. And now let's look at example 2. So we are getting farther away from the initial point, which was 0. Now we're calculating at 5. Okay. And then as you can see here, so the Euler sequence creates the Euler sequence, and then I manually do a fourth order Richardson, right? So the difference from the example 1 here is that I'm applying a fourth order Richardson on the original Euler sequence, and then I plot it. So let's run example 2. So here I'm plotting the error, and as you can see, the error is not that good at the beginning, like compared to the previous case. This is not the error, this is the exact value. After like 5 to 10 terms, we had a very good convergence, but here it's not like that. We have to go farther away, like 60 or 50 terms to get a good error. And the reason is that now in example 2, we are calculating at a point x equals 5, which is much farther away from 0 than 0.5, right? So as we get away and the interval gets larger and larger from the initial point, the error grows and we need more and more iterations, right? But then in example 3, again the same thing, y prime equals minus y, and the initial condition y of 0 is 1. Here I'm going to use the method that we just wrote, including the trick that we're using for changing the initial condition when we are passing an array of x values. So here I'm creating an array from 0 to 50. I want to find the value of the solution y at 1000 points from 0 to 50. So I have a y exact array and y Euler array. Exact solution is e to the minus x, so I write a for loop and calculate them. And the Euler is OD Euler, right? So here what I'm doing, I'm using this, so I'm not using this trick. I'm using Euler method with Richardson at 100 point, okay? So what this does is that it always calculates the solution based on the original initial condition. And that's exactly the plot that I have here, okay? So this is the, let me just see, example 3. So in example 3, what we're doing is that we're calculating the, here, so I'm going to write, calculate y of x always based on y of 0 equals 1. So we always use the original initial condition to find the value of the solution at some later point x, all right? So this is example 3. And if I run it, you see what happens. As we get farther and farther away, the error gets bigger and bigger. So the blue one is the exact solution, the red one is the Euler solution, which is good for like up to 25. But as we get farther away from the initial point, we see that we get this error, which is not good at all. All right. Now obviously if I put, instead of 50 I put 100, we should see that the error even grows more and more. Yes, and it's actually very bad. It's like incredibly bad. Okay, it suddenly diverges. So what we need to do, we need to basically, instead of using the original initial condition that causes this problem, because the error is proportional to the length of the interval, we look at example 4. Oh, one other thing is that here the Euler method actually does the fourth order Richardson. So if I don't do that, the error even gets worse and worse. So let's run example 3 one more time. So in the example 3, this red one is the Euler sequence, which has a fourth order Richardson acceleration. So if I go back here and remove that Richardson acceleration, we expect to get even bigger errors at the points that are even closer to the, yes. So this is the original Euler solution without any acceleration, calculated at 100th term of the sequence. As you can see, it's just good for small values of x, like 1, 2. At 50, the error is very large. If we do a fourth order Richardson and evaluate that sequence at 100th term, we see that the error is actually pretty good up to 25, x25, but then we still get this error. Okay, so what I'm going to do is let's return back the Richardson acceleration. I'm going to look at example 4. So in example 4, again, y prime is minus y, the initial condition, y of 0 equals 1. I'm setting up a timer here, and now I'm trying to find the solution from x equals 0 to x equals 50 at 1000 points. The exact solution is e to the minus t, okay? And now I'm passing in the array, right? So I'm calling this Euler method instead of this one. So if I pass one double value, it calls this method. If I pass an array, it calls this method. And this method, because we're passing an array, it applies the trick that we use to change the initial conditions at each step to make sure that the length of the interval remains small for all the calculations, for all the x values in this interval. Okay, so this is our final case, and we hope that this solution should give us a better solution than the previous solutions, right? And okay, so let's run example 4. Maybe let me just run example 3 first. So this is Euler with fourth order Richardson without the trick, and now example 4. This is Euler with fourth order Richardson with the trick, and the trick is that when I'm trying to calculate the y at some point, I use the previously calculated point as the initial condition. That way, the length of the interval that I'm solving over that interval is very small, so the error is guaranteed to be small. And as you can see, it actually removes all the errors. Now let's see what happens with this trick when we go even farther. Let's say 80. Yeah, there is no error. So this method seems to be very effective, and you should always try to use this adaptive method or this clever trick, because for solving differential equation we can always start from some initial condition, initial point, find the value at a very close point with good accuracy, and then use that new point as the initial point to finding the later values again and again. And as you can see, it's a very effective way of removing the error. Okay, so this was the final trick that we can do with Euler. So Euler was not good because it had a very slow convergence, because the error was the behavior of the error was 1 over n. So we accelerated with the Richardson. Let's say if I apply fourth order Richardson, the error should be 1 over n to the fourth power. Okay, And then the other problem was that, but the error also is proportional to b minus a, right? Because error proportional to h, so b minus a over n. And now we're saying that, okay, if I want to find the value of the solution at an array, we can use this trick to, after finding the solution at some point x1, we use that point as the initial condition to find the later point, okay? This guarantees that the length of the interval always remains small. Now let's look at another example. Here I have y prime equals y over x, and y of 1 is 2. All right, let's go here. Let's call this, for example, example 5. I can just copy and paste this one. So in the example 5, y prime is y over x. So x and y goes to y over x. All right, y prime is y over x. And then this is my derivative function, and then I create the ODE solver, pass in the function and the initial condition. What was the initial condition? Y of 1 is 2. Y of 1 is 2. And then I should calculate the value at y of x for x greater than 1. Remember, just note that this function y prime has a singularity at x equals 0, so we cannot solve for values basically less than 0 or between 0 and 1, right? We should always solve for values that do not, for intervals that do not include this singularity. So we are going to go from 1 to, let's say, 10 with 100 points. So the exact solution is 1 over, oops. The exact solution is 2x. Y is 2x because at 1 is 2, and y prime is 2, which is y over x. So the exact solution is just a linear solution, 2x. So 2 times t. And we apply it to the x array, and then the Euler solves for the Euler, and we plot the exact and the Euler. It doesn't take much time. It's like I think we're still running example 4, so let's run example 5 here. 12 milliseconds is very fast, and we shouldn't plot it on a log scale. Okay, so we just plot it on a linear scale, and yes, it's exact. So the blue curve here, so I'm going to turn the marker on the figure number 1, which is the Euler solution, the numerical solution. Line width of the Euler solution to 0. So the Euler solution only has markers, and the exact solution only has, so let me also reduce the number of points to 20, for example. Okay, so this is the solution as a function of x values. Okay, let's go and put this here, and at 1.5, for example, we have 3, which is exactly the exact solution. Okay, but let's also look at the error. So in order to look at the error, so let me just create a new example. Let's call this example 6. In the example 6, what I'm going to do, I'm going to basically do the double error, new double x dot length, and then for int I equals 0 and len equals x dot length, I less than len, I plus plus. Error I is basically math dot abs of y exact at I minus y Euler at I. Okay, And now I'm going to just plot the error. And so let's turn the marker off and let's run example 6. Let's see what happens. So the error remains very small, 5 to the e negative 6, right? And let me just increase the number of points, let's say 200 points. 7 negative 5. Let's say 2000 points. 2e4. So in our method, as we see that as we increase the number of points, the error gets larger eventually, because that's just the computation error, the accumulation of the error. But now let's say we take to 20 points, and instead of doing calculating the solution based on the adaptation of the initial condition, we try to use it, calculate the solution at each point using the original initial condition, x dot length, and then here basically let's see, y Euler at I is Euler ODE solver dot Euler at xi. So as you can see, there's not much difference in terms of the error. We get relatively same error for both different approaches, directly using the initial condition or using the array iteration by changing the initial condition at each step. But if you get farther away, let's say 100, let's increase the number of points. So with the Euler method, this is the error. So if I don't do this and use the array solution, this is the error. So again, as we can see in this case, we see that the error is comparable. There's not much difference, right? But we have to always keep this in mind, that changing the getting farther and farther away from the initial point basically increases the error eventually, even if we do Richardson acceleration. And that's just because the error is eventually proportional to the length of the interval. So let me just plot this. So x values, let's call this error. And it's always pretty fast. It doesn't take much time, like 10 to 14 milliseconds. And let's copy this, put this in the PowerPoint. So this is our error. And this is the evaluation of the function from 1 to 10. And we see always that there is a good match between the exact solution and the accelerated Euler method. So there are more examples, and please stay tuned. In the next lectures, I will explain those examples and also go back and move forward with the other methods, such as midpoint method and the Runge-Kutta. And the final word here is that RK4 is eventually what we're going to use most of the time. Even though we're looking at the Euler as a very simple method, it's most of the time, or almost all of the time, we use RK4. And we will see that RK4 doesn't even, it generates a sequence that doesn't even need acceleration, because it's already, the error is already very good. Like, it's the original error for RK4 is already 1 over n to the 4th power, for example. So we don't even need to do any acceleration. And it makes the RK4 more efficient in terms of numerical computation. I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.